Hey everybody, so this is the follow-up few slides on uncertainty and expectation values. So where we left off, I gave you a couple questions to think about. So we talked about the expectation value of energy for a harmonic oscillator system, or a couple of different harmonic oscillator systems. And so one of the questions that I wanted you to think about is, can we define other expectation values besides the energy? And if so, how do we calculate them? Can expectation values change with time? Can the uncertainties change with time? And finally, if I don't know how to express my wave function as a combination of energy eigenfunctions, what can I do? Okay, so let's talk about the first couple of questions. Can there be expectation values besides the energy? And if so, how do you calculate them? Same question for uncertainties. So I hope this, by now is maybe more of an obvious question than the other ones. And in fact, a lot of you might remember that this is actually one of the postulates that basically, well, yes, first of all, the answer is absolutely yes. We can define expectation values for anything that we can measure. So remember, every observable has an operator. So here's our generic observable O and its corresponding operator O hat. And so the expectation value of O is nothing more than this integral. And so this is actually one of the postulates. And then if I wanted to think about the not the expectation, but the uncertainty, right, remember I'm going to need the square root of O squared minus, I need first to calculate the expectation value of O squared and the expectation value of O, and then the uncertainty is square root of expectation value O squared minus expectation value O, that whole thing squared. Okay, so both of these things are well defined for any observable in quantum mechanics because they all have expectation values. So the key is to be able to set up this integral or these different integrals and take them. And so just a couple of little notes about these integrals. Number one, the expectation value is going to be an actual number, something that corresponds to the average over the observations you make in a set of experiments. So it's going to be a definite integral. So my notation up here is a little bit vague. You notice that I have an indefinite integral. And the reason for that is because the range of the integral is going to be different depending on what your system is. And we talked about this a little bit. You need to think physically about the domain in which your system can exist. So we had our particle in a box was a very limited domain because of the potential associated with the system going to infinity at the edges of the box. Our system really could only exist between 0 and L, where L was the length of the box. So if we were talking about a particle in a box system, we'd want all of our integrals to be between 0 and L. Our harmonic oscillator, on the other hand, could exist anywhere between negative and positive values of infinity, and so that would be our range of integration there. We'll see some other systems too, some angular systems that are defined between 0 and 2 pi, or 0 and pi, and that sort of thing. And so we will have appropriate ranges of integration depending on the system. Okay. So hopefully it's clear that the answer is yes, you can have expectation values of all of the observables, and you can have uncertainties in those things too. So let's be a little bit more concrete. Let's talk about another expectation value besides the energy for a system that we know and love, the harmonic oscillator. So let's actually try to make this as concrete as possible. Let's say that we are interested in the expectation value and the uncertainty and the bond length if I have a diatomic molecule like HCl here and its ground vibrational energy. And one thing that I want to remind you is that we defined our coordinate system for the harmonic oscillator such that r equals 0 corresponds to the equilibrium bond length. So here's a little schematic of HCl. The equilibrium bond length happens to be 127.4 picometers. It's kind of a funny system of units, but that's also the same as 1.27 angstroms or 0.127 nanometers, whatever you feel most comfortable with. So when r and our coordinate system is equal to 0, then really the bond length is this equilibrium bond length. So r equals 0 really maps to 127.4 picometers as the separation between H and Cl. Okay, and so when we calculate an expectation value of r and the uncertainty in r, then we should think about it relative to this equilibrium bond length. Okay, so that hopefully that's clear. All right, so how are we going to do that? Well, we actually need to calculate this integral, right? Because we know that our energy eigenfunctions, they are eigenfunctions of the energy operator. They're not eigenfunctions of the r operator, and they're not eigenfunctions of the r squared operator. So we're actually going to have to do some integration here. So let's pull up our Mathematica notebook. And this is on Blackboard under course material. It's called the Harmonic Oscillator Mathematica Notebook. Hopefully very obvious name. And so let's actually calculate these integrals in Mathematica. And so before we calculate these integrals, let's actually just look at the ground state wave function. So I'll remind you that up above in this notebook, we've already defined a function called psi, which takes two arguments. The quantum number is the first argument, and that's always going to be an integer, 0 through infinity. And r is the actual variable, which corresponds to the bond length. And r equals 0, again, corresponds to the equilibrium bond length. So let's just plot that function between values of -6 and 6. And so again, and one other thing I'm going to remind you of that's maybe slightly less obvious, but this axis, our r-axis, of course, has dimensions of length, but we've chosen a very peculiar unit system. So you don't want to think about r equals 4 as something like 4 meters or 4 picometers or 4 nanometers even displaced from the equilibrium bond length. These are some natural units of length. We could figure out their conversion to meters if we wanted, but we're working in a natural unit system, which is defined so that the Planck's constant times square root of the force constant divided by the reduced mass is all equal to 1. So we'd have to do a conversion to figure out what 4 natural units of length are in picometers, for example. And we could do that calculation, but let's not worry about it right now. Okay, so this is simply the ground state energy eigenfunction here, and what we're going to be doing is we're calculating to get the expectation value of r, right? We want to take the r hat operator, which is really just the variable r, and first multiply it by the energy eigenfunction. So let's actually plot that too. So let's just look what r times the first energy eigenfunction looks like. Right? It looks like this. So not surprisingly, it's going to turn the energy eigenfunction, which is even and peaked at r equals 0, into a function which is odd, meaning that the right-hand side is the inverse of the left-hand side, and also a function that goes to 0 at r equals 0. And that's because the r function, of course, goes to 0 at r equals 0. It goes to 1 at r equals 1. It goes to -1 at r equals -1, and so on. So if you just think about this product carefully, then its graphical representation will start to make more sense. Okay, so that's what the function r times psi naught is equal to. And of course, the actual function that we're integrating over is not just r times psi naught, it's psi naught star times r times psi naught. So take a second to convince yourself that psi naught star is the same thing as psi naught, because the energy eigenfunctions of the harmonic oscillator are pure real functions. But once you've convinced yourself of that, you can go ahead and plot that whole integrand psi naught times r times psi naught. So let's do that. Okay. And so basically what's happened is I have taken the probability density function and multiplied it by the r function. And so it looks very much like psi naught times r, just the values are squared. The values of psi naught are squared at each point and then multiplied by r. Okay, so that's going to be the integrand for the expectation value of position, and some of you may realize that, okay, well, I've got a function which is basically odd between negative infinity on this side and positive infinity on this side, right? Every point on this side of the plot is exactly canceled out by a point on this side of the plot, and so that means if I take the area under the entire curve, right, it should actually add to 0. And so let's just see if that happens. So right below my plot function, we've got an integrate function, and we simply want to integrate right, our psi naught times r times psi naught between very large values of negative r to very large values of positive r. So I just argued that this integral should be 0 based on its anti-symmetry, and let's see if Mathematica agrees. And Mathematica agrees. Fantastic. Okay, so that takes care of the expectation value of r. So if we go back here, the expectation value of r equals 0. What that means is that if you took, many copies of hydrogen chloride, all described by the ground state energy eigenfunction, and you made a measurement on each one of them of the bond length, and took the average of all your measurements, your average would be the equilibrium bond length. Remember, because r equals 0 corresponds to the equilibrium bond length. So expectation value of r being 0 means that the expectation value of the bond length is the equilibrium bond length. Okay, so that's actually kind of encouraging, right? That tells us that there's some meaning to this equilibrium bond length, which can be physically measured. Okay. So now let's look at the expectation value of r squared. Okay, and so I'm going to do what I did first. I'm going to actually just plot for you r squared acting on psi naught. Right, so this is the first part. This is basically the part of the integrand right here. And so what do I get? Well, I get basically whatever the shape of psi naught is multiplied by the parabola r squared, right? And again, the parabola r squared, of course, is 0 at r equals 0, but increases quadratically with increasing r and with decreasing r. And so the shape of the resulting curve, looks how you would expect it to if you think about the form of these two functions multiplied together. Okay. And of course, the full integrand is going to be not just r squared psi naught r, but psi naught of r times r squared times psi naught. So let's go ahead and look at that as well. Okay. So now if you look at this function, this is actually different in a very important way from the integrand of the expectation value of r alone, right? This is not an odd function where all the points on the right-hand side are canceled by the points on the left-hand side. This is actually an even function. I've got points here which are positive, and I've got points here which are positive. So then if I think about taking the area under this entire curve, it's clearly not going to be 0 unless there's something way out here in the tails of the function that I can't see, and that's actually not the case. The function actually goes smoothly to 0 as r goes to positive infinity and as r goes to negative infinity. So really, this is going to be the main contribution to the integral, and the area under this curve is clearly not 0. So let's see what it is. So I'm simply going to take the integral over psi naught r times r squared times psi naught r. Okay, and so the expectation value turns out to be 0.5 and that's again in these natural units of length. Okay, and so this tells us important things, right? So if I make many measurements on many independent systems, all in the ground state, right? My average bond length is going to be the equilibrium bond length, and the average bond length squared is going to be a half of a natural unit. So basically that tells me that the uncertainty in the bond length is going to be the square root of expectation r squared minus expectation of r squared. And that's going to be basically equal to square root of 0.5 natural units of length squared. And so the result will be 0.707 plus decimal places natural units of length. That is the uncertainty in R. Okay, so so there you go. So there's one concrete example of calculating an expectation value and an uncertainty for a quantity other than the energy. And so I still used my energy eigenfunctions, you'll notice, right? I actually stuck in energy eigenfunctions here, but actually I hope this also illustrates the answer to this other question, which is what if I don't know how to express my wave function as a combination of energy eigenfunctions? What if I just have a function and I can confirm that it's a valid wave function, but I don't know how to express it in energy eigenfunctions? Well, you can still do exactly the same procedure that we did with Mathematica, right? All you need to know, if you know the function and you can take its complex conjugate, then literally what you want to do is numerically evaluate the product of your operator acting on that function that you have, and then multiplying that result by the complex conjugate of your function and integrating. And so, typically you're going to be able to do that by hand or on a computer in just about any case that you're likely to see. So this is really not a big deal if you can't express your wave function as a combination of energy eigenfunctions, because for most expectation values, you can't just simply pull out eigenvalues in your integrand anyway. Okay. So the next question is, can my expectation values change in time? And so what I've done is I've just rewritten my expression for the expectation value in a slightly more suggestive way, where I've included not just the spatial dependence of my wave function, but also the time dependence, because generally speaking, our systems actually can change in time. The wave function does depend on time, and we see in certain special cases, like when you're in an energy eigenstate, that certain quantities are static in time, like the probability density function. But in general, quantum mechanics cares about time. And so it's a natural question to ask, will my expectation values change in time? And so before we get into the mathematics of that question, let me just try to touch on what that physically means. So if an expectation value changes in time, then if we go back to this kind of experiment that our expectation values are supposed to map to, right, where I've got many copies of my system and I measure some observable on each copy of the system. Well, if the expectation value changes in time, then the result that I get from such an experiment would depend on when I made it. So that is to say that if the expectation value of energy were depending on time, then in order to get one result, right, I'd have to make the measurements simultaneously. These independent measurements would have to be made simultaneously. Otherwise, right, I could imagine that that the results of my experiment would be wildly different depending on how long I waited. So that's your question: is do you think that's actually the case, or do you think it matters? So let's actually remember one little system that we've looked at before, which is this electron in a box. And in particular, let's think about our wave packet describing an electron moving in our box with infinite wells with some average momentum and starting out in some fairly localized position. So we've got a simulation of that system now at our disposal because we wrote it. So let's actually look at the probability density evolve in time. Okay, so here's a movie of the Gaussian wave packet's probability density function as a function of time. And this red curve is the initial probability density function. So you know that the probability density function quantifies the probability of measuring the particle at a particular position, right? So at the initial instant of this simulation, of this computer experiment we're running, right, you are very likely to find the particle localized at x equals 200, plus or minus about 25 units of length. Is that the case at this instant in the movie when I'm talking? It seems that the probability has drastically changed. So let's watch that again, and just I'm not going to talk. I'm just going to let the movie play out for a minute. Okay, so I think it's clear from that movie that the probability density can certainly change in time, which means that the probability of finding the particle can change in time, which I hope also implies to you that certain expectation values, like the expectation value of position, it can change in time. And then one more time, let's watch the movie. You'll notice also the Gaussian is getting fatter as it travels. Once it actually hits the wall, it becomes very hard to decipher what's going on, but you can clearly see before it hits the wall, the Gaussian packet is getting wider. So that means the uncertainty in position is also changing in time. So the answer is definitely generically yes, expectation values can change in time, energy can change in time, but this is a very, sort of subtle and slightly complicated issue. Actually, I'll say, without a risk of bad pun, this is a complex issue. And what I'd like you to do is actually work out how the expectation values can change in time under certain circumstances and how they won't change in time under other circumstances. And maybe you'll get the complex joke at that time. So let's actually consider two different systems. And these are a little bit simpler to work with than the harmonic oscillator system. So this is back to our particle in a box system. So you've got an electron in a box of length 10. And you can work again in natural units. And in natural units, h bar is going to be equal to 1. So you could have a box of length 10 natural units. H bar would be equal to 1, and the mass of your electron would be equal to 1. That might help simplify things if you need your energy eigenvalue. Okay, and so here's two different systems, right? You've got system described by the wave function big psi 1, and that happens to just be a state purely described by the first energy eigenfunction. So here's the spatial part right here. Square root of 2 over 10 sine of pi x over 10. That is the first energy eigenfunction. It's a properly normalized energy eigenfunction. And here's its time component. Remember that the complex exponential of negative I times the energy eigenvalue divided by h bar times t. That is the time dependence of the first energy eigenfunction. Okay, so that's system 1. And then system 2 would be described by this wave function here. So now this is a superposition of two different energy eigenfunctions. Energy eigenfunction 1, which has, this is its space part right here, square root of 2 over 10 sine of pi x over 10. This is its time part, exponential of negative I E1 over h bar times t. And it's so this is the whole energy eigenfunction psi1 of x and t right here. And this is its weight in the superposition, square root of 1/2. Okay, and then over here we've got energy eigenfunction 2. And so again, within these parentheses is energy eigenfunction 2, square root of 2 over 10 sine of 2 pi x over 10 exponential of negative I e2 over h bar times t. That is the full psi2 of x and t, little psi2 of x and t, the full time-dependent energy eigenfunction. And this is its amplitude in the superposition, or its weighting in the superposition. So just make sure you're clear on the fact that this coefficient square root of 1/2 is different than this coefficient square root of 2 over 10. Right? Square root of 2 over 10 is what we call the normalization constant for the energy eigenfunction, and square root of 1/2 is the amplitude in the superposition. Right? So make sure that those are conceptually distinct in your mind. Okay, so for those two systems, here are two different expectation values that you can calculate. Expectation value of energy for state described by big psi 1 and state described by big psi 2, and expectation value of position for state described by big psi 1 and state described by big psi 2. So the question is, do these expectation values depend on time for either of these systems? And if so, how do they depend on time? So that particular question is also going to be important for your midterm. So I encourage you to work through these expectation values and try to understand the consequences. All right. I hope this was helpful. And again, I'm looking forward to seeing everybody in class on Wednesday. And have a great start to your week.